Spoofing isn't just an abstract threat.
Pull up.
It's happening right now in a lot of places all over the world. What happens if your aircraft was subject to GPS spoofing? Will it still find its way? And after the aircraft has left the spoofing area, will the GPS work properly again? Will all other systems in the aircraft still function properly? One incident that is currently under investigation and where spoofing probably played some role is that of the Azerbaijan Airlines flight 8243. The flight was supposed to go from Baku to Grozny, but was shot at and subsequently crash-landed near Aktau in Kazakhstan. The interim report suggests that the aircraft may have encountered spoofing during its approach to Grozny, which prevented it from successfully landing there. So what exactly is GPS spoofing and how does it differ from jamming? Jamming and spoofing are two different threats to satellite navigation with different effects on the aircraft and on aviation. In jamming, a disturbing signal blocks the reception of the GPS signals entirely. You can think of it like this. Imagine you're listening to someone whisper important information into your ear, but then a baby starts screaming right next to you. No matter how hard you try, you can't hear the whisperer anymore. Of course, this is somewhat simplified, but that's essentially what jamming does to GPS. But spoofing is much more deceptive. Instead of blocking the real signal, imagine someone perfectly imitating the whisper, but giving you wrong instructions instead. You can hear it very clearly, but now you've got misleading information. It doesn't just block GPS, it tricks it into believing it is in a different location than it actually is. Now that we understand the basics of spoofing, let's talk about why it's even possible in the first place. And the answer comes down mostly to signal power and how the GPS receiver works. By the time a GPS signal reaches a user, it is incredibly weak. Satellites transmit signals with a power similar to that of a standard old-fashioned light bulb. Now imagine placing that standard light bulb in space over 20,000 kilometers away. By the time its light reaches the Earth, it would be incredibly faint. And GPS signals experience exactly the same effect, arriving at receivers with extremely low power. But despite being so weak, GPS receivers can still track those signals. They do this by generating a local copy of the signal and looking for a match in the received data. This process, called correlation, allows the receiver to receive and decode the data that are coming from the satellite and ultimately measure the distance to those satellites. And based on those distances, the receiver can then calculate its position. But here's the weak point. For receivers to generate a local copy and recover these signals must be publicly known, which also means they're easy to replicate. This is what makes GPS spoofing possible. If you can generate a signal that looks just like the real one, you can trick a receiver into believing it is tracking an authentic signal. And by carefully crafting and manipulating these fake signals, a spoofer can make an aircraft or any receiver really believe it is pretty much anywhere they want it to be. Now that we understand why GPS signals are vulnerable, let's take a look at what happens when an aircraft actually gets spoofed. What effect does it have on the aircraft? And what effect does it have on air traffic control? GPS spoofing is most problematic when an aircraft relies heavily on satellite navigation. For large commercial aircraft like all those Airbus and Boeing aircraft, it's not as simple as just fooling GPS, because these aircraft rely on multiple redundant navigation sensors. The aircraft fuses the GPS with the onboard inertial reference system information, so the so-called IRS, which measure the aircraft's movement independent of GPS. So if a spoofed GPS signal suddenly makes the aircraft jump to a different position, the IRS would detect that mismatch and reject the fake GPS position. In addition, most aircraft also use conventional radio navigation, such as DME-DME or VOR-DME positioning, providing an additional way to cross-check that information coming from GPS. If sufficient ground-based navigation infrastructure is available, the aircraft can easily continue to navigate without relying on satellite navigation. But even when an aircraft's navigation system can detect and reject spoofed GPS positions, spoofing can still cause unexpected secondary effects that impact flight operations. One issue observed in real-world cases is that spoofing can trigger false alerts of the ground proximity warning system. Pull up, pull up. Parts of that system use the GPS altitude directly, meaning that a spoofed low altitude position can falsely activate the terrain warning. This can distract the crew, obviously, or worse, lead them to initiate an escape maneuver, and in areas without terrain but with a lot of other traffic, this could cause serious issues. After leaving the area where the signals are spoofed, usually most receivers recover and function again normally. However, in some cases, the GPS receivers fail to recover, and that leads to a loss of the required navigation performance, or the RNP capability, of the aircraft. This can prevent aircraft from flying certain routes or approach procedures that rely on the availability of GPS-based navigation. Another effect of spoofing affects the surveillance part of the aircraft. Since ADS-B relies on GPS for obtaining its position data, spoofing can cause an aircraft to transmit an incorrect position via ADS-B. And this is exactly what real-world ADS-B spoofing maps, like the one from Sky Data Services, are tracking. But this also raises concerns, especially as some aviation roadmaps propose replacing a lot of the radar infrastructure with ADS-B-based systems. But GPS isn't just used for position and navigation. It is also the primary time reference for many aircraft systems. If the GPS time is spoofed, it can alter the time and date of the onboard clocks of the aircraft. This can then disrupt data links, as some communication systems reject messages if their timestamps significantly differ from the actual current time. And some of those data links are important for air traffic control to fulfill their tasks to keep aircraft safely separated from one another. And unlike aircraft, air traffic controllers do not rely directly on GPS to track the traffic. Instead, they primarily use radar surveillance, at least where radar coverage is available. Radar operates independently of GPS, determining an aircraft's range and bearing to the radar station using its own signals and the aircraft's transponder reply. This means that a spoofed GPS position of an aircraft has no effect on the radar track, allowing controllers to issue vectors and guide the aircraft safely. But what about areas without radar coverage? In remote and oceanic airspace, like the busy airspace over the North Atlantic between Europe and the United States, controllers often rely on ADS-C, that's Automatic Dependent Surveillance Contract, instead of the broadcast, which is ADS-B, for aircraft position reporting. Unlike ADS-B, which continuously broadcasts an aircraft's position, ADS-C works through a dedicated two-way communication link between the aircraft and air traffic control. The key difference is that ADS-C does not simply transmit raw GPS position data. Instead, it reports the aircraft's best position estimate. Typically, that is a fusion of multiple navigation sources rather than just relying solely on GPS. This makes ADS-C far less vulnerable to spoofing, as it usually excludes incorrect GPS data. But of course, this only works if a data connection between the air traffic controller and the aircraft can be established without the aforementioned synchronization issues. But even while ATC may still see an aircraft, that doesn't mean operations are unaffected. Without GPS, aircraft typically lose their RNP capability, meaning they might not longer meet the required performance regarding navigation for a given airspace. This could force aircraft to change routes, fly at different altitudes, or require ATC to increase the separation to other traffic in order to maintain appropriate safety levels. Beyond en route challenges, quite some instrument approach procedures require GPS. A well-known example that received quite some publicity is Tartu Airport in Estonia, where the arrival route required the aircraft to have GPS. So when significant GPS jamming started in the region, Finnair had to discontinue their flights to Tartu until a conventional DME-DME-based approach that can also be flown without GPS was published. And here is another challenge. ATC radar itself does not indicate whether an aircraft has lost GPS or RMP capability. Thus, the controllers might only find out when pilots report navigation issues, creating extra workload, especially if multiple aircraft in an airspace lose GPS at the same time. So, while radar-based ATC remains largely unaffected by GPS spoofing, the loss of GPS and RMP capability can still create challenges, especially in high-traffic airspace. So far, we have seen how GPS spoofing can affect aircraft navigation, air traffic control, and the operations. But how can pilots and controllers actually recognize when spoofing is happening? And more importantly, what can be done about it? For pilots, GPS spoofing might sometimes be not so easy to identify because there is no direct warning that the GPS signal is being manipulated. Further, GPS spoofing and jamming may often seem quite similar, as both can cause a GPS receiver to stop providing valid position information. However, spoofing has some distinct characteristics that pilots can recognize. One of the most effective ways for pilots to detect obvious spoofing is by cross-checking different navigation sources. All modern airliners integrate multiple navigation sensors, so if GPS shows one position but the inertial reference system or radio navigation aids disagree, it is a strong indication that GPS is compromised. But monitoring the different positions is obviously not a task that the flight crews are routinely performing all the time. Beyond inconsistent navigation data, spoofing can trigger a range of unexpected system behaviors. Some key warning signs include ADS-B reporting errors. Spoofed GPS positions can cause incorrect ADS-B transmissions. If GPS is unavailable or rejected, usually some form of ADS-B related error is the first indication to flight crews, as it usually requires GPS to function as specified. But the ADS-B reporting issue also occurs in the case of GPS jamming. So it's not such a good way to distinguish between jamming and spoofing. Then another indication is a GPS receiver failure. Some receivers stop providing valid position outputs entirely, again similar to what happens in jamming. GPS-related errors often become apparent if the aircraft detects obvious issues in the receiver, for example, through cross-checking different navigation sources. But as we already discussed, the loss of GPS can also trigger additional warnings, such as unable RMP messages. It can have an impact on the runway overrun prevention systems. As these systems are also driven mainly by GPS, they may become unavailable too. Previously discussed already, unexpected GPWS alerts. Manipulated GPS altitudes to low heights can falsely activate those terrain warnings. Incorrect time displayed. Spoofing can shift the onboard clock and even the date. One particularly strong sign of spoofing is if the system date appears to be almost 20 years ahead. More precisely, it should be 1024 weeks or about 19 years and 7.5 months in the future. That's because the GPS week number in the navigation message only runs up to 1024 before it resets. Receivers are developed to not jump back in time, so if the spoofing is done in such a way that it lags a bit behind the true current time, the receivers would jump those 1024 weeks forward. One way to prevent this is, if your aircraft can do that, switching the timing source from GPS to internal. Datalink failures. Some communication systems reject the messages if the timestamps are significantly off. Unexpected aircraft maneuvering. If the aircraft is actually following the spoofed position, unexpected turns may occur. It is important to note that GPS spoofing effects vary between different aircraft types and avionics systems. Thus, if you're flying, always refer to the technical guidance and procedures from your aircraft and avionics manufacturers to understand how your specific aircraft may be affected and what actions should be taken in case of GPS jamming or spoofing. While pilots have some means to identify spoofing and mitigate part of the effects, technology plays a key role in reliable detection and prevention of these attacks or their consequences. Several solutions are being developed to enhance GPS resilience against spoofing. One of the simplest defenses is using multi-constellation receivers. Instead of relying solely on GPS, these receivers track signals from multiple global navigation satellite systems, or GNSS in short, such as the European Galileo, the Russian GLONASS, or the Chinese Beidou, making it a bit more complicated for a spoofer to manipulate all those signals consistently. However, real-world research suggests that this might not be very effective. High-power spoofers can simply saturate the receiver, blocking out the authentic signals entirely and leaving the receiver only tracking the spoofed signals. For more advanced protection, so-called controlled reception pattern antennas, or SERPAs, can be used to filter out spoofed signals. These antennas use directional filtering or beam steering to block signals that do not originate from legitimate satellites. Currently, SERPAs are restricted under ITAR, limiting their use in aviation. But this restriction is set to be lifted in late 2025. However, aviation receiver certification takes time, standardization and certification must be developed and completed before these solutions become widely available. So, despite ongoing efforts, it may still be years before SERPAs can be widely integrated into civil aviation. While spoofing remains a challenge, combining pilot awareness, ATC surveillance, and advanced technology can help reduce the risks. Finally, let's now revisit the doomed Azerbaijan Airlines flight. The transcript in the interim accident report shows that the pilots were unable to perform the RNAV GPS approach into Grozny due to GPS interference, likely spoofing. While descending towards Grozny, the transcript also indicates that the ground proximity warning system activated at least twice during seemingly normal operations. A behavior that, as we discussed, is consistent with the aircraft being affected by spoofing. Because they could not fly the RNAV approach, the crew had to revert to the NDB approach, which has significantly higher minima. This resulted in the aircraft having to execute a missed approach. The pilots then requested vectors for another approach due to the continued loss of GPS. The transcript further reveals that there were multiple communications between Grozny Tower and the flight crew, with both sides trying to establish situational awareness about the aircraft's actual position and the next steps on how to get them on the approach to Grozny. Without jumping to conclusions on the ongoing investigation, the voice recorder transcript clearly shows that the aircraft suffered severe navigation issues, very likely due to GPS spoofing. If you're interested in reading the full report and make up your own mind, I've added a link in the description below. You can use AI tools to help translate it from Russian if needed. As GPS spoofing continues to evolve, the aviation industry is working on solutions, from multi-GNSS tracking to very advanced SERPA antennas and receivers, so that GNSS-based navigation can be used safely. But those solutions do take time. Certification, standardization, and adoption across aviation won't happen overnight. Until then, awareness and training remain critical to reducing the risks of spoofing in aviation. Thanks for watching, and see you in the next video.